All right, so well, let's see if I can get you to participate right away. Here are uh, two kind of early founding people of computer science. Does anyone know who they are?
Yeah, it's Ada and Tori.
All right, so this is Ada Lovelace, uh, who was sort of like working out like these things on paper before like there's even any conception of a mechanical computer. But she was also in touch with this person named Babbage, who was trying to build something to kind of do logarithm tables and stuff. And then the person on the right is Alan Turing, who maybe you guys know more of since, for example, there was a movie about him. But at some level, he sort of formalized a model of computation to ask a very abstract question of whether there are things that can't be computed. And somehow this abstract model he came up with actually is what von Neumann based his design on, and it is sort of clear in modern computer architectures. Okay, so that's just fun. Let's get this going. Um, so let me get the administrative stuff done first. Okay, so this is graduate algorithms. As you guys know, uh, the most important thing is that we have this class website, which is some ginormous PDF, and it has everything. And the goal is to make sure it has everything. And if there's any confusion, we should make sure the edits are propagated into the website and it'll keep everyone on the same page. So, uh, that's where the homeworks will be. The schedule, is all laid out. Um, Initially, and all the lecture notes, as well as like links to, for example, when I post this video online, that YouTube link will be in the lecture notes at the end of the chapter. You can already find last year's videos already up as well. In fact, the document is the same document as last year's, but just replacing all instances of 2023 with 2024. And also we have a fresh new set of wonderful TAs and stuff I'll get into. The biggest difference between this year and last year, and I usually make some changes, but relatively small, but the biggest difference is that last year we're on that more standard Tuesday, Thursday schedule that met for a little bit longer. This year we're on this Monday, Wednesday, Friday schedule that's only meeting for 50 minutes. So, you know, the plan is basically just to chop up last year's lectures and then see how it goes. Maybe a little more into the class, I'll have a better sense of what I can and cannot do in 50 minutes, and I'll make more adjustments. But at least beginning, we'll just go through the same sequence, and we might have this sort of awkward thing where in the middle of the Wednesday class, we sort of end one chapter, start the next. So right now, I don't see a better way to go about it, but if you guys have ideas, of course, I'm happy to hear. Okay, so the main highlights, and I'm going to let you guys maybe read the syllabus over the next few days, and I'll also take questions now. But otherwise, I just want to highlight a few things to look out for. Uh, Maybe the most important thing is our TAs. So we have Tian and Hao Yu, and I'm very excited about them. At least our meetings so far have been very smooth. So and they're like the good guys. I think over the course of the semester, you'll get annoyed with me, but they will be the ones who help you out along the way. So make friends with them and so on and so forth. Um, they've already figured out their office hours on Tuesday and Monday, in part because our homeworks will be due on Wednesday. So we thought that would be best. And I'm personally trying to figure out whether to do it on a Friday or Monday morning, but I'll get that posted um uh soon. Um okay, other highlights include so the class is roughly divided into thirds, which is two midterms and a final. And they're all cumulative. In part, the idea is also like the first midterm, like a lot of people are taken off guard because it's sort of a new format. So the subsequent midterm and final will give you second and third chances at the material. Um, we have weekly homework. Right now, I've just sort of pasted all the homework from last year as like a default, but I'll probably replace most of them. So all of those have this sort of tentative disclaimer. But it'll give you some sense of what we did last year at least, and a reasonable expectation for this year. We have lots of like policies just to keep things running smoothly, and try to catch like all the little things that come up. For example, there's various homework problems over the course of the semester, and you'll get graded for the problems on an individual, I mean, per problem. And at the end, we're just going to drop the lowest 1/5 of the scores. So this way, I don't know, if the dog ate your homework or something, okay, that would just be gobbled up in this 1/5. If there's some, I don't know, weird dispute about regrading or something, hopefully this will soften some of these outliers that come up for everybody over the course of the semester. It's also partly to emphasize that, okay, some problems might be trickier than others. We don't expect people to do perfect or anything. The real thing is just to keep learning and keep going. So we don't ever expect any kind of perfection. Maybe another unique policy in this class is we have a late homework deadline, which I think is 4 days after the regular deadline. So I think homeworks are going to be due on Wednesday nights at midnight. And then we have until Monday to do it late. And I think we just take off 35%, if I remember correctly. We should check with the syllabus. And then we'll just grade from there. So you can still get most of the points. And this is actually in conjunction with the fact that we are actually going to on Wednesday night, as soon as you all turn in your homework, maybe on Thursday, we're going to put up solutions, and we're actually going to pick out some of your solutions, whoever we thought was best, to try to kind of encourage you guys to write cleaner solutions and make our lives easier. But so you can actually look at the solution, decide if what you submitted was a complete disaster or something, and even redo it if you want to. Again, the point is like, look, if you're learning, and even if you make a mistake, that's okay. If you learn from the mistake, that's what I care about most. So you can still recover most of the homework points. Okay, so things like that. But check out the syllabus, and I'm happy to take questions right now. Here's one question. Okay, I'll get to. Oh, well, that's the same question in the chat. Then I'll read it out loud, which is, when will the first homework be posted? And I think it actually is posted. I think I actually removed the disclaimer saying that this is tentative, but if not, the current homework 0 is what we are going with. It was the same as last year. Okay. Oh, what else? We've already set up a Piazza. We always have some debate about whether you guys still like, or you all like Piazza. I'm not 100% sure, but the default is a Piazza. And so the Tianin, how you are going to check Piazza like regularly, but not necessarily. Sure, I'll also follow up on that. Regularly, but not necessarily like continuously. So they might check like a couple of times a day or something on Monday through Friday. They're not necessarily going to check in on the weekend and stuff like that. So we'll just have like a reasonable hours where you would expect the TAs to check in on Piazza. Okay, great questions. Okay, so let me do some more questions. Could you please explain a little more about the part where we could make up for homework points? Okay, so this is just the fact that it's like a leniency or a second chance policy. So basically, homeworks are due on Wednesdays, and there's a late deadline on Monday. And before the late deadline, we actually post the homework solutions, so that if you had this sense that, oh, I really didn't do the problem correctly, you can actually revise your solution, resubmit it to Gradescope, and that'll just be treated as a late solution. Okay, so that's just it. Is there any restriction to the language to be used for homeworks, like C++, Java, or Python? Actually, we would rather you not use any of those languages in particular. So I guess we'll get into it soon. But we're going to be working in a sort of pseudocode, a more high-level thing, because at some level, as I'll discuss a little more upcoming, our goal is to try to develop ideas in a style of thinking that's more independent of the particular language at hand, right? So I'm trying to practice your thinking skills, kind of your communication skills at a little bit more of a conceptual level. Okay, in fact, the thing I'll be most interested in is clarity. is the clarity of your solutions. And I think that, okay, right now we haven't started yet. It's a little bit ambiguous, but as we get into it, I think it'll become clear what the expectations are. There's also examples for some of the homework problems and stuff like that. The first couple of weeks are always a little bit awkward too, as we kind of get used to how things are, and that's just how it is. But every year this happens, and every year we figure it out. Okay. In this course, are we counting from 0 or 1 for indexes? You can do whatever you want, but just make it clear. So you'll see in my notation, for example, I'll write, oh, this is an array 1 to n. Then it's clear the first index is 1. Okay. So most important thing is being clear, being communicating. And that's really my goal, is to help develop this more conceptual level, sort of a liberal artsy view on computer science. Okay. Any more questions? And we'll also have opportunity for questions kind of each of the next couple of classes, including Friday, where I'm much more fun in person. Or I hope. Okay. All right, let's keep going then. All right, let's talk a little bit about computer science. So this lecture might be a warm-up or redundant for some of you, but not necessarily all. And besides, it's okay to take it easy at the beginning. I'm sure we'll ramp up soon enough. So I'm going to talk about 2 things that you guys should all know, even if you don't have much background in computer science, at least implicitly, if not explicitly. Okay. So let's start with the simplest thing, just counting. Okay. 1, 2, 3. So, all right. Pop quiz. How many tallies are drawn on this screen? 23? Anyone else? All right, a couple more 23s. Yeah, okay. So this is indeed 23. So some people here are very good. But at the very least, that exercise should have been very painful and maybe had you questioning this class. The obvious point here is that the right-hand side is a much more efficient form of representation than the left-hand side, right? These tallies, these caveman tallies. Okay, the left-hand side actually has a fancy name. It's a unary, just as many dots as you're counting to. And the right-hand side, as you guys all know, is decimal, right? And so what's really the power of the decimal notation is just 2 digits. I can, capture any number between 0 and 99, right? That's 10 squared numbers. If you give me 10 digits, I can capture any number between 0 and 10 to the 10 minus 1, which is, I don't know, 10 billion, I'm not sure. Okay, right? And okay, you all know this, of course, right? But having the k in the exponent, right, and being able to express more and more was relatively small amounts of information, number of bits, right? This is right. This is really our first example of what's called combinatorial explosion. Okay, 10 to the k is really talking about how many combinations you can make with k characters, each one of those 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? We take it for granted, but this is implicit in everything we'll do all semester. Okay, let me talk about something else, which will make you wonder, how is this a graduate education? Okay, yeah, question.
Yeah, I was just wondering, okay, can you please go to the previous page?
Yeah, sure.
Is like for this one, why aren't we minusing the numbers that start with 0? For example, 0, 0, 0, 1, 2, 3, something like this, for decimal notation to the k.
Oh, sure. We are. So good point. So the 10 to the k numbers in particular are going from 0 to 1 to 2, all the way up to 10 to the k. Let's say k is 10, so 10 to the 10 minus 1. But that's still 10 to the k different ones.
Okay.
That's all I meant to say.
Thank you.
Yeah. Okay. So that's a simple, basic example of combinatorial explosion that you all know. You all have dealt with all your life. Okay, here's another thing that many of you have may done before. I did it in my like second or third grade class. Usually it's like before we go to recess, which is like the only good time of school. And for some reason, before we're let out, our teacher would be like, "Okay, I'm thinking of a number between 1 and 100." And the game is we have to try to figure out what the number is. But the rules are we guess a number, and the teacher would say, "Oh, the number I'm thinking of is either over or under that last guess." And so if it's over, we choose some number that's bigger. If it's under, we choose some number that's smaller, and we try to figure out this number between 1 and 100. Eventually, we're let out into the wilderness. So, okay, I thought we'd play that game. You guys can shout it out if you want. So I am thinking of a number between 1 and 100. Your goal is to identify a number with as few guesses as possible. Okay, 50, and I will say over. 75, I will say under. 63, I will say over. 69, well done. I will say under. 65, I'll say over. 66, I'll say over. What's going on here? 67, come on guys. Over. All right, 68, you got it. Okay, so it took you 8 rounds to identify the secret number. Okay, so as all of you seem to infer, at least until the very end, which is a little disappointing, there is a slow way to play this game, right? But a very simple way. The slow way is to go 1, 2, 3, 4, 5, all the way through to 100. Synchronization there. Okay, that's fair. And I think you all realize not to do this. And then there's a fast way, right? The fast way, you're not really trying to guess the number. Of course, I'm not going to choose 50. I'm not a moron, right? But what you realize is that if you choose 50, you reduce the number of options by half, no matter what, right? So we went like over. So okay, sorry. So you went to the right, and then we went under. Oh, okay. Let me just think I got a little too cute here. Okay, so we have this kind of tree, right? Where right or left, there's only going to be 49 options left. And then there's going to be like 25 options left, and then like 12 options left, and so on and so forth, right? And what you're really doing is you're not trying to guess the number. You're trying to eliminate the options, right? Now, as you get all the way down to the bottom, right? There's some question of how many rounds do you need? And at some level, that is, what is the height of the tree until I start getting to very limited options, like 1, 2, 3 down here. All right, how many rounds do you need in the worst case? Yeah, so you need log 2 of n, which for us is log base 2 of 100, right? Okay, how do we figure this out? Well, okay, maybe one way is to write Okay, this is log base 2. Well, okay, yeah. Who wants to tell me what log base 2 of 100 is? Okay, we know it's at most 7 because 2 to the 7 is like 128 or something. We should all know this like the back of our hands. On the other hand, we know it's at least 6 because 2 to the 6 is 64, right? So it's somewhere between 6 and 7. Which is it? So it's actually 6 because if you divide 6 times, if you take 100 and divide it by 2 6 times, you'll get a number that's smaller than 2. It's bigger than 1, but it's smaller than 2. So you know the number of options left is less than 2, and it has to be an integer, so that'll get you 1. Yeah. Okay, good. Of course, I will never, ever, ever really care about plus or minus 1 in this class. Okay. 1 round is nothing for a computer. Okay, good. So really the point of this exercise is to point out that there's 2 really basic mathematical functions that even if you don't work with on paper, you definitely understand the intuition. One is the exponential function. 2 to the n takes 2 and multiplies it n times. Before we talked about 10 to the n, but 2 to the n is, of course, the same. Okay. On the other side, we have logarithms. Okay. So the logarithm base 2 of n, it's how many times do I have to take n I'll come back to that question in a moment. How many times do you really have to take n and double and half it until you get to 1? Or conversely, if you kind of look at this, maybe the definition in the book, it's that unique number where I take 2. How many times do I have to double it, which might be fractional, to recover n? Okay. And then 2 comes up very often in computer science, but there's different bases. So this kind of Euler's constant, log base E of n, sometimes called the natural log, um, comes up pretty often. In real life, we often like to do things base 10, so you often see log base 10 of n, but you can really have log base b of n for any value b greater than 1. There was some question about there are some nodes that rounded up and some rounded down. Is there a convention? That's, I think, in relation to this, there's no convention. It's arbitrary and it won't make a significant difference. Maybe over the course of this lecture, we'll start getting into what I kind of suggest when I say significant difference and trying to tell the difference between the forest and the trees. Okay. Okay, so 2 basic things: exponential, logarithm, digits, over-under game. Of course, you all likely know this quite intuitively, right? All right, here's maybe another example to try to demonstrate the power of logarithms. I tried to think of, okay, what's the biggest possible number in the world? And I thought, okay, number of atoms in the universe. Okay, this is, what's the name? There's a name for this. Okay, it's in the notes. There's a name for the number of atoms in the universe, and I forgot it. It's named after some English scientist who actually, I think, also was a person who set up the experiment to test Einstein's theory. There was like an eclipse with Mars, and so the light was going to bend around Mars if Einstein was correct, and he was the one who set this up. Eddington's number. That's right. I think he also invented one of these Google Scholar metrics, like the H metric or something. Anyway, all right, he's a very interesting guy. All right, so the number of atoms in the universe is 10 to the 82. Okay, which I guess is as big a number as I can think of. So the log base 2 of the number of atoms. Okay. So I'll plug in 10 to the 82. right? Okay. Now, how do I break this down further? Yeah, Eddington number. Thank you. Oh, in high school, I learned this trick where I guess if something's in the top right corner, I can just pull it out of the logarithm, right? I mean, that'll also be clear if you went back to the definition above. So 82 log base 2 of 10. Okay. And roughly what is log base 2 of 10? Or what's it between? Yeah, so I know it's bigger than 3. 2 to the 3 is 8. I know it's less than 4. 2 to the 4 is 16. Somewhere in between. So this number, I looked it up, is very close to 3.32. Okay. What's 82 times 3.32? Three times 80 is like 250, 240. Anyway, it comes out apparently to like 272.39. Not that I did it myself, but yeah. Okay. All right. So this is pretty amazing, right? Because 10 to the 82 is a massive, massive, massive number. Like I cannot wrap my mind around the Eddington number. But 272.39 is quite modest. I kind of know what that number looks like, right? So you can literally go from atmospheric astronomical numbers to reasonably modest numbers with one logarithm. Okay. To make this more dramatic, we can take this even further. Okay. What if I took the log twice of the biggest number I could think of? Right? Well, we'll just plug this in. Log base 2 of 272.39, which is roughly what? Or what's it between? Yeah, we know that, oh wow, we got exact, okay, someone's doing some Google searching. Okay. Um, so 2 to the 256 is 2 to the 8, right? And then 2 to the 9 is 512, so it's somewhere in between. It's probably closer to 256. So approximately 8, and I trust this number 8.089. Pretty close to 8, right? So if you take a logarithm twice, right, of the biggest number I could imagine or think of, the biggest number named after someone maybe, you get down to 8. So that's really how powerful logarithms are. That means, to put that in perspective, we played this over-under game between 1 and 100. And it took us a few rounds. But I could have said, oh, I'm thinking of a number between 1 and the Eddington number. And we could have reasonably played this game. It would have taken 270 rounds, which is kind of boring. But it's possible, right? So you can actually almost identify an atom in the universe using binary search. Okay. So much for that. So my claim is that this class is largely about identifying the difference between these two regimes. 2 to the n, which is, combinatorial explosion, right? Things are kind of out of control. There's so many different choices versus binary search, where I can take a ton of items, but if they have structure, for example, if they're ordered, and I can do things like picking out the median and going left or right, picking out the median and going left or right? Now my algorithm is taking time, something more like log base 2 of n, right? See, what this really represents, when something looks like 2 to the n, it means there's lots of combinations and not much structure. There's all these combinations. We don't know which, and we don't know how to navigate it. Log base 2 of n means, oh, there's a very strong structure to the n items. And I can navigate it extremely efficiently, right? In the over-under game, you're finding a number between 1 and 100. You're not checking all the numbers. You're actually skipping almost all of them, right? So logarithms really reflect structure. And 2 to the n exponentials reflect complexity. Okay. And so this class is largely about kind of understanding what this means in maybe more concrete or complex situations. Okay. So, all right, let's talk about maybe a more involved problem, one that you didn't know when you were 6 or 7 years old, but also you may still know quite a lot about this. All right, so let's talk about sorting. I know many of you seen sorting before, but maybe not everyone has, so it's very hard for me to skip this. It's a good introductory thing as you get used to how these things go. Okay, so sorting. Very simple. I'm going to give you n comparable items. For simplicity, I'm just doing numbers. And I want to put them into sorted order, right? So if I kind of think of the items as sort of this wavy line on the bottom, I want to sort of straighten out this line. Okay, the items should be rearranged in sorted order. So just to make sure we're on the same page, I am going to ask you all to help me sort this modest list of numbers. Okay, so I want to put this set of numbers in sorted order. What comes first? Great, 1. All right, what comes next? 2. Okay. Oh, sorry. 2. 4. Indeed, 5. 7. 6. It's not so easy. 7. Another 7. 8. 9. 9. 11. All right. Okay. All right. No big deal, right? Just sorted a bunch of numbers, and we avoided most of our synchronization errors. Okay, good. Of course, nothing special. All right, so this was sort of that was sort of an algorithm, right? I'll call it human sort. I'm pretty sure this is how everyone would normally, naturally sort numbers if they just had a pile of numbers on a table in front of them. Okay, so you're looking at a bunch of numbers and you need to sort them. What is sort of the first question you would ask? Yeah, you would ask, what's the smallest number, right? That's exactly what we did. And we said 1. And at least, I mean, I did it out of habit, but I'm sure most of you would too. I marked off 1 to remember we already checked out 1 off. Okay. And then what would you ask next? Okay. What comes second? You would ask what comes second, and that would be 2, right? And you start making this list on the bottom, right? Okay, very simple. I call it human sort, but it has more fancy psychopathic names like, I think selection sort or something. It doesn't really matter. You should never use this algorithm. Okay. But this is sort of at some level our first iterative, or at least it's one of our first few algorithms, right? So the idea is to build a sorted list from beginning to end. And for each number that we build, I scan the entire list of inputs, right? I scan the list, I find the smallest number, I check it off. Then I scan the list, find the second smallest number, I check it off. Each time I'm scanning and finding the smallest number that I haven't checked off yet. Okay. So what we want to do is ballpark how long this takes. right? We need to start ballparking and quantifying these things so we can start distinguishing one algorithm from the next, right? So we're going to start measuring these things. Okay, so we're going to do just a simple calculation. I think this is the natural way to try to analyze it from first principles. So in general, you're given n inputs, and I want to calculate roughly how long it takes. So one way to break that down is say, oh, okay, I know that it's sort of like a nested loop, right? The outer loop we'll call an iteration. So how many iterations are there? There's n iterations, okay? And the time it takes to do one iteration, which produces one more number in the output, it is proportional to the numbers, that list of numbers I need to scan, right? And how many numbers were there? Oh, okay, maybe that's already in the chat, I can't tell. But we scan all the items all over again. Okay, so n passes, each pass I scan all the items, right? And I multiply that together and we get n squared time. Okay? And that's just a ballpark, right? I mean, at some level, you know, what I'm really doing, right, is okay, I scan the list, each number I look at, I check to see if the number is checked. And if so, I compare it to the smallest number I've seen so far. And if that number is smaller, then I replace it. It becomes my new smallest number I've seen so far. And I move on to the next number in the list and I check and things like this. You have a question? Welcome. Put the question in the chat. Yeah, question. Go for it.
So in the iteration, the scan part, are we also scanning the already sorted part of the list for each iteration?
So in each iteration, are you already scanning the sorted part of the list? Well, the way we did it, which is we checked off items as we go. So once we took an item, we checked it off. We didn't really need to look at the numbers we've already taken because the real thing is we've marked off the numbers we've already taken.
Yeah. But
that said,
here,
I think, yeah.
Yeah, it's n times n. So it's not like n times n minus 1 plus n times n minus 2.
Oh, that's also a good point. So I'll come to that point in a moment. So to close that previous point, each of these quote unquote steps, I'm doing more than one thing. I'm looking at a number in the list. I'm seeing if it's checked. If it's not checked, I'm comparing it to the smallest number I've seen so far, which maybe I'm holding locally in memory, right? So it's more than one step. Is it 2 steps? Is it 3 steps, 4 steps, 5 steps? I don't know. And that's only in pseudocode, right? At some level, that's going to get compiled to a bunch of stuff in registers, right? It's going to change some pointers, swap something in. It has to do like 10 things just to load in the 2 numbers before doing a comparison. Okay. And meanwhile, at some level, we don't want to worry about these details, right? Those details may depend on the exact programming language. It may depend on the exact computer. And it's not really going to change how we're thinking about the problem. It's not really going to inform our algorithm design. So I'm not really too worried about exactly what a step means. I think we can basically agree it's some constant number. The real issue is the n. How does this scale as n? Now, another point that came up is that, oh, well, once I checked off something, maybe I can skip it or something, right? In which case, oh, is it like I look at n numbers the first time and then n minus 1 numbers the second time and then n minus 2 numbers the third time and so forth? Or maybe can I make a data structure where maybe I have a list and whenever I take a number, I remove it from the list so I don't even scan it again the next time? So let's say that I did try to be more aggressive and I looked at this sum, right? Where I'm observing that the list is getting smaller and smaller. Depending on how you implement, maybe it would look like this, right? But what is this? Is this really much smaller than n squared? So it already kind of came up in the chat. It's actually pretty close. It's at least n squared over 2. It's actually, there's an exact one. It's n times n minus 1 over 2. But Since I don't care about constants anyway, I'm going to just say, oh, it's at least n squared over 4. What's the easiest way to see that it's at least n squared over 4? There's a trick. I know you can look it up in Wikipedia and get this very exact formula, but that's a waste of time. What's the easiest way to see that this is at least n squared times some constant? Induction? No, not induction. Induction will get you actually a more precise argument. That's a good guess. And if I wanted a more precise answer, that might be a good way to go about it. But I don't want a precise answer. I want a really quick estimate, because really I'm trying to design algorithms. So I don't want to spend too much time doing too detailed a calculation. I need to quickly recognize at a high level what's going on. And then I can keep thinking about the algorithm. Okay, so here's a great trick, $1 million trick. Maybe not an exaggeration. Let me give myself a little space. Okay, somewhere in the middle, there's n over 2 in this list, right? Okay, how many of these numbers in the list are bigger than n over 2? N over 2. So there's at least n over 2 numbers that are bigger than n over 2. N over 2 times n over 2 is at least n squared over 4. Very easy, right? But simple tricks like this, it's not about being precise. It's about understanding what's going on and making it kind of intuitive, being able to tell the forest from the trees. So at some level, this style of thinking is also something we're going to practice a lot. Now you might ask, oh, is n squared over 4 a good estimate? Well, obviously n squared is an upper bound, right? So I'm not off by at most a factor of 4, and I'm not going to sweat a factor of 4. I'm going to move on with my life. Okay. So we can codify this, right? There's this thing called big O notation, right? It's going to codify this idea that I'm not worried about constants, at least on first pass, right? We're really focused on designing algorithms at a high level, understanding conceptually what's going on. Okay. And then once you really start implementing things in practice and you know this is really what you want to do, then you can start worrying about more low level details. But you got to get the big picture down first. That's what we're focusing on in this class. So big O n squared, what I'm saying is that there's some constants, capital N and C, so that for all little n bigger than big N, it terminates in at most Cn squared steps. Right? So C might be 100. I don't know. I don't know what it compiles down to in the registers. And besides, even if I did, by the time I figure out exactly what C is, that computer is going to be twice as fast. Right? A new computer will come out. So I'm not worried about C. Okay? The exact C, depends on these things that are external to algorithm design. Okay? But really what's going on, right? When I hide the constant, I can focus on the big picture, on the conceptual things, on the real structure of the problem. And that's a starting point for trying to develop a general theory of algorithms. The key point is general, right? Can we come up with ideas that somehow give us a principled way to think about making algorithms, right? General, that's an exciting word, right? We want to take a world full of 1 billion moving parts and shrink it to something that's of limited complexity, and you can get this unified point of view. On the same computer, would you expect an algorithm with running time n squared over 2 to run twice as fast as one with n squared? That's the question. So I think the real issue is it's very hard for us to determine exactly n squared over 2, right? The constant is hard because there's going to be some constant depending on the compiler or something. But what sometimes happens, for example, given 2 algorithms with the same big O, the simpler one will just work much, much better. So if you're really worried about somehow getting a better constant and you make your algorithm very complicated because you think you're improving the constant, you may find that your longer, more complicated algorithm, you think it has a better constant, but it doesn't. Okay, it's a little bit mysterious. So ultimately, if you have a couple of good candidates for n squared and stuff, you don't have much intuition for which one is which. At that point, you might test it. Also, you should figure out if even that's the bottleneck in your bigger system. Right? Okay. So this is interesting. We're down to, so the class properly ends at 12:20, right? Okay, I've never really taught in this time thing, so okay. Then what I will do is introduce the next part, and then we'll pick up from there next time. I'm assuming you don't want me to go 10 minutes over starting from the first lecture. So, okay. Okay. So, so, so we did this n squared thing for sorting numbers, which is maybe something we've all done before, but we also introduced this big O notation, which is actually a big deal. Okay. The question we always want to ask is, can you do better? Every problem we ask, can you do better? Our goal is to come up with good algorithms. Okay. And this is sort of an interesting question. I know many of you may know the answer, right? But it's interesting from this point of view. N squared is a very natural number because it represents comparing every pair of numbers, right? And from a naive point of view, you might think, oh yeah, if you're going to sort n numbers, then of course, every pair of numbers needs to be compared with each other. That's kind of a very natural way to think about it, right? So when we say, can we do better than n squared, we're actually asking kind of a conceptually interesting question, which is, can I actually sort all the numbers and make sure all the pairs are kind of correct relative to each other without comparing every pair of numbers explicitly? Because if I did, that would surely take n squared time, right? So that's actually kind of an interesting conceptual question, even if you all know the answer and take it for granted. Okay. So yeah, let me maybe try to lead into where we're going so that we can get off to a good start next class. So we're going to take maybe a different perspective. Okay. So one question when you're asking, can you do better? Can you do a better constructive algorithm? There's sort of an opposite side of the coin that you can ask, which is, oh, something easier than constructing a sorting list is double checking a sorted list. Okay. So if I give you a list of n numbers, how long does it take to double check that it's sorted? Right? So an adversary claims these are sorted, and you want to verify that numbers are indeed sorted. How would you do that, and how long would it take? All right, but how? What would you do? The sooner you answer, the sooner we're done. What would you do? What was the first thing you would do? Yeah, exactly. So you can compare the first two numbers. Is it smaller? The next two numbers, is it smaller? Is it smaller? Is it smaller? Is it smaller? And they all need to be yes. And then, of course, if A1 is smaller than A2 and A2 is smaller than A3, then A1 is smaller than A3 because of this. Well, the fancy word is a transitive property, but really, you all know this. So, right? So we actually have a much faster algorithm to double check that something is sorted. Okay? So that's where then I'll leave off today at this question. Our intuitive way of sorting takes n squared time, but maybe I do know I can double check a sort is an n time. And, can we even get the running time down to n or something, right? That's okay. I don't think we can verify any faster than n time. I think that's the best. So I don't see us doing better than n time because how are you going to sort n numbers without even touching all of them? But, where in between these two values is the answer. Okay, so we're going to end up next class trying to be very precise. Oh, that's actually a very good question. Can you use binary search? Okay, actually, this is a very good question. I know I'm over time, but it's such a great question, I can't help myself. could you have done better than n? Why can't you use binary search? So suppose there's one mistake in here, right? Maybe the mistake is here. This is actually wrong, right? A2 is actually bigger than A3. It's like, oh, can we use binary search to find this? It's kind of tricky because you would think, oh, if it kind of feels like it's sorted, if it's not sorted, isn't it something like binary search? But the mistake is the point of the mistake is sort of like arbitrary, right? You can't play over under. You can't pick a point problem in the middle and ask which side is there a mistake. So it's not as structured as we like. So okay, so we can't do binary search. So next class we'll try to figure out if we can do better than n squared. Can we even get down to n? I don't know. You already know. But that's where we'll start next class. So thanks, and I'll keep hanging out here. Right. So we did some kind of over under, little binary search last time, and we started sorting. So we talked a little bit about the natural way to sort, and we talked about this n squared running time. But I think most significantly, we also use this to introduce this big O notation, right? This emphasis on asymptotics as opposed to exactness, especially since exact things aren't even well defined across computers, right? So this big O notation is really the point of emphasis, and it's a slightly different perspective because you're a little less exact. But in my opinion, you're going to focus on the most important things this way. So okay, so n squared is from this sort of picking one number at a time, and of course sorting is a pretty well known problem. So this exercise wasn't completely necessary, but sometimes right. So can you do better than n squared? And maybe there's some natural reasons why you might not think you couldn't. For example, n squared represents comparing every pair of numbers. So in general, right, you might be looking at a problem, you say, how do I solve it? Right? And there's some emphasis on correctness there, right? If you have an algorithm that solves something, very likely it should somehow conclude that the output is correct. So something a little bit simpler then would be just given a solution, can I even double check the solution is correct relatively fast? It's just like a different point of view. It might not seem super necessary for sorting because it's, again, something that we know really well. This is sort of just setting some foundation for more sophisticated situations later, right? But just conceptually, at a high level, you're worried about correctness. Is this a situation where you can even verify correctness, right? And not necessarily, well, probably if your algorithm is going to conclude its output is correct, then your algorithm is going to take as long as the best possible algorithm to double check something is correct, right? So verification is something that's a little simpler, and it's just sort of, coming up with questions to poke at things and try to understand things, and so forth. Okay. And I think it'll be motivate a little bit because it was also meant to be a transition to the next idea coming up. So, right. So we concluded last time saying, okay, we can sort n numbers in n squared time. And we can also double check that a list of numbers is sorted in n time because I only actually have to do, I only have to compare the adjacent pairs in this long list, right? And then transitivity says, oh, if the adjacent pairs are okay, then they're all going to be okay, right? It's simple enough, but it does suggest, oh, maybe you don't have to compare every number with each other. You certainly don't to verify that a list is sorted, right? So that's where we sort of ended the lecture. It's like, okay, there's one relatively simple algorithm that takes n squared time, and there's also a relatively simple verification algorithm that takes n time. Now, the best sorting algorithm, can we get it down to n, or is it going to be stuck at n squared? So on and so forth. Okay. All right, so as I sort of build up to more sophisticated algorithms, here then is sort of an intermediate problem. Okay? It's a little bit easier potentially than sorting, a complete jumble of numbers. So suppose the input was like half sorted. The first half of the numbers was sorted, and the second half of the numbers were sorted. Right? So that's more structure than just any arbitrary set of numbers. And so now my question is, I give you this special case, this nice structured situation. What is the fastest way to output a fully sorted list? I give you the two halves are sorted, and you want to output a fully sorted list. Okay, so someone put out running time, but why or how? Or what would you do first? Either way.
Start from the first number.
Okay, here's the first number.
Maybe have a two pointers, both starting from the list of each pointer pointing to the start of the
Okay,
each range.
so we can start at we're kind of looking at the beginning of each of the sublists, and then
just make a new list, and then just what you can do is like maybe see which one is the smallest, and after that we can just make that pointer point to the next number or the next index in the specific array, and then continue this
excellent.
unless
So
we exhaust the whole list.
yeah. So I might first compare 1 with 4. Okay, 1 is smaller. And then we'll move our pointer over. Now it's looking at the 2, compare 2 and 4. 2 is smaller. Okay, move the pointer on. Now I'm comparing 5 and 4. 4 is smaller, right? Move the next pointer, and so forth, right? At some level, this is actually, to some extent, the same as our human sort as before. We're picking out the smallest item at a time. But we know, because the input is actually structured, if I'm trying to get the smallest number overall, I only have to look at the beginning of the two lists, right? To find the second smallest number, I advance one of the sublists appropriately, and at the top of one of the two lists will be the second smallest number, right? At some level, this is still human sort, or what I called human sort on Monday, except because the input is structured better, you can actually do it much faster. You do this all the way through, and you end up, each iteration, you only look at two numbers now, and you're going to check off a number from the input and add an input number to the output. So now you have n iterations, and you're really only comparing two numbers in each iteration. So you're spending O1 time, which is to say a constant amount of time per iteration, right? The time I spend is independent of the size of the input. And overall, we get this linear time. It might be 10 n operations, 20 n operations. I'm not too concerned. Okay, simple enough. So, okay, we're trying to figure out how hard is it to sort two numbers. We now know that you can take two numbers, two sorted lists, and actually output a sorted list in time that's much more comparable to verifying, right? Like ON is pretty awesome running time. So, okay, we're going to give a name to this. This is sometimes called merging two lists. Okay, I have two sorted lists and I merge them together. I kind of think of like a zipper, kind of zipping things up. And out comes a sorted list. I think this pseudocode makes it look way harder than it really is, right? You're just going one by one all the way through. Things to keep track of is that you're going to finish looking at one list before the other. And at that point, you need to just dump out the rest of the list. That's what these last two while loops are. They're just processing the remaining elements. Simple enough. So, okay. So we are going to try. Okay. Good. So at some level, I know that if I can sort the two halves of the list, or if I had the two halves already sorted, then I can put it together very, very fast. right? So that's maybe an idea for an algorithm, right? So now I'm looking at the general case again. I have n general items, and I want to sort them. So, okay, here's maybe a general template. Maybe it's asking for too much, right? But if I can kind of like delegate the work and say, okay, let me try to sort the first half and get the second half sorted as well. And if I have those two things in place, then I can merge them together. Right? That seems like an okay high level approach. I know I can merge things together, so let's just figure out how to get the first and second half sorted. Otherwise, merging is like free practically. I mean, ON is so cheap. So, all right, but the obvious question is, how do I sort the first half? Right? I'm trying to make a sorting algorithm, and great. All I've done is said, oh, I'll sort the first half. That seems like cheating, doesn't it? Okay. So how then could I try to sort the first half of the algorithm?
Maybe you can consider like the array. It's like a sub-problem. Like so, the problem was to maybe have the list sorted. So what you can do is like divide the array into two halves, and we also run into the same problem. Like for each half, we want to sort the list, and we can recursively give it a call, unless we run into some base case, or unless we are left with
Okay, so
just one number.
I can imagine trying to do. Can we use bind? Okay, come back to that. Can we try to do something similar to the first half, right? Which means, okay, I can kind of expand that out and say, okay, I can look at the first half and divide that in half. And then maybe I can figure out how to sort the first half of the first half and the second half of the first half, right? And then I have another question. Okay, how do I sort the first half of the first half? It feels a little bit like I'm kicking the can down the road, right? It also feels a little complicated when we talk about it that way. So there is a magical word that we can say here that was put in the chat, right? That lets you do this, but without like the cognitive burden. Okay, so this is called recursion. I am going to, the magical word is recursive, but I'm making some kind of algorithm. The algorithm needs to deal with part of the input. To deal with the first part of the input, I'm going to use the algorithm that I'm designing. Same as the second half. I'm making some kind of algorithm. I need to deal with the second half, and I'm going to just call my own algorithm. I have that in some ways I haven't even finished designing yet to deal with the second half, right? But conceptually, that's something kind of really nice. Oh, my algorithm is supposed to sort, so why don't I assume it sorts the first half correctly and just let it deal with it? And let me just assume it sorts the second half correctly. Let it deal with that. And then I know how to deal with two sorted sublists, right? There's a sort of leap of faith where you say, oh, my algorithm's just going to be able to deal with anything smaller, right? And at some level, presumably take care of a lot of details because merging is quite simple. It's not clear at what point this algorithm becomes very complicated because I'm just like somehow magically punted. It feels absolutely like cheating, right? But the wonderful thing is, this is in fact completely sound as long as we carefully use this thing called induction. Okay? Only briefly about a comment. I don't think we have anything called binary sort at this point. Maybe binary search, but searching is a little different than sort. Okay, so we're going to try to do recursion, and I'm going to try to expand on what I mean by recursion. Okay, I know that that sorting is a relatively simple thing, but in a much more sophisticated problems, this is going to be a very powerful tool. So, okay. Oh, I should have erased this. Okay. Well, okay. So the first thing, I erase this. I'll hide it a little bit. Okay. When making a recursive algorithm, okay, I want to do this magical trick. Where say I'm trying to make an algorithm. How do I deal with a small part of the input? I'm going to use the algorithm I'm making. That makes like no sense at some level if you think about it in certain ways. So what are we going to do? The most important thing far and far away, and something that you'll always be required to do in this class, is to write out what we call the recursive specification. You should be doing this for your code anyway, right? But you're trying to define a function. So let's declare what that function is. Okay? So I'm going to say, right. So what I want to do is I want to very clearly define what I'm trying to accomplish. Okay? And this is going to act as some kind of really formal contract. And that's going to justify the correctness of the algorithm overall. Okay? Now, when we do programming, it's basically there's an input and there's an output, right? So I always just start with giving it some name. I'll call it sort. Guess we'll probably come up with a better name later. And it takes as input an array of numbers, right? Okay, so I've sort of like given it a name and I kind of declared some input, right? Of course, this is how you would write your code. And then I'll do something relatively mundane. And I'll say, okay, given n comparable elements, A1 to n, right? So remember, person reading your thing may not know the context. But the input is now fully specified, right? In an array, but that's okay, right? But I said n comparable elements. It's very important that the elements are comparable. Otherwise, how are you going to sort them, right? So it's important to specify really the input that's going in, okay? And next, we need to describe the output, right? What are you returning? And it needs to be specific. It needs to be, because I'll expand on it in a moment. So maybe I'll let someone else complete this. So I might start the sentence saying, okay, given n comparable elements A1 to n, how would you write the rest? Yeah.
So we need to define like a base case scenario.
You're coding. We're not coding yet.
Okay.
We are declaring what our algorithm does. And this is actually a habit that I really want us to embrace. Don't jump into the code yet. Focus on what you need, what goes in and what goes out. Okay, returns a reordering of the indices or return n-sorted elements. Okay, so I'm going to go with the second one. So it's very natural basically to say, given blah, blah, blah input with certain properties, returns blah, blah, blah output with certain properties. Sometimes there's a little bit more, but those components are almost always there. So it returns maybe an array of the n elements in increasing order. Okay. And maybe that's like a relatively long version of this exercise. Okay. We basically just restated the problem. And that's often the case. There's not necessarily too much, detail and cleverness required at this stage. But what does this accomplish? So, one sec. Oh, that's not good. Okay, it's okay. Okay, one sec. I screwed this up a little bit. Okay, so let me flash. I didn't manage my space very well, but oh well. In sorted order. All right. Okay, so what are some of the things we accomplished this, right? So It declares the input and output of the algorithm. That's clear. That's the goal. But what it really does is it creates some kind of contract that the algorithm has to fulfill. First of all, you should do this anyway, besides recursive situations. If you're coding on a team, it needs to be clear exactly what you do so that your teammate doesn't have to read your code. Okay? So we're declaring a contract that we have to fulfill. Why is that so important for recursion? It's important because when I now delegate to these subproblems, I know my algorithm is going to fulfill this contract. We didn't just write some kind of like code comment. We actually set up the induction hypothesis to prove our algorithm is correct. There's really not as big difference between a recursive specification and induction hypothesis. I have trouble thinking of a situation in this class where there's any difference. Induction hypothesis sometimes comes up in a discrete math class. It's a more mathematical setting. So this is some kind of, more programming and applied and doing stuff version of induction, right? But by setting up this contract, you're now, when we go to implementing next, you know what your algorithm is going to do on the subproblems, and you're able to actually reason about this. Okay, but you have to actually establish this initially, or else you're kind of cheating and you won't be quite sure. Okay? I know this is, again, sorting is something you've all seen before, but there's going to be more sophisticated recursive problems coming up, where in fact a lot of the thinking occurs at the level of this contract, this recursive specification. You might first write down the most natural recursive specification. It's more or less the problem that's given. And you might find out you can't quite implement it. You actually have to make some changes. But the design stage is to go back to the recursive specification and try to change that. That's often where the biggest idea is. If you get the specification, this induction hypothesis correct, it's pretty tough to mess up the implementation, at least if you're careful and you're not in too much of a rush. Okay, so really a lot of this thinking occurs exactly at this stage. Right. So, okay. All right, so now when we implement this, okay, and this is, I know some of you kind of leaped into the implementation, but we declared a specification first, and then we implement these. Okay, and so, okay, I want to make sure that I handle all cases correctly. There's always some bottom base case, right? So, something when the input's only 1 or even 0, of course, there's very little we need to do. We don't have to do all this fancy recursion and stuff like this. Oh, there's one element, let me just return the input. Of course, it's sorted. Same if it was empty. So this first line, don't forget it, but it's often very simple. Okay? When the input's very small, these problems often aren't very complex. In fact, often for almost any problem, you can just be lazy and say, oh, if n is at most 10, do brute force. Brute force might be bad, but brute force on 10 elements takes constant time no matter what. So, n less than equal 1, I'll just return a. Okay. And now here is the code from before. Here m is just picking out the median, right? N over 2 rounded down. I could have been rounded up. It's not a big deal. And then I call merge sort on these two halves. Okay. Okay, I've renamed it merge sort. It's not just called sort anymore. And what's the key point? The key point is I know that those subcalls are going to satisfy the recursive spec by induction on n. So the key point is that the numbers 1 through m, especially if m is rounding down, is always going to be smaller than n. My recursive spec is simultaneously my induction hypothesis. We're going to do induction a little bit more slowly next. But it comes my induction hypothesis. And I assume if I'm worried about a particular input size n, the algorithm works for everything smaller than n. Okay. that first half, 1 through m, is smaller than n, I just assume it works. And I don't have to think about it beyond that. I don't have to, imagine it going into the first half and splitting in half and splitting in half and splitting in half. It's just by induction, it's done. Right? So it's a great relief. Same with the second half. And then merging things together was pretty straightforward, right? You just pick off the first half. There's not much controversy. Okay. But to justify this magical step where we do the subcalls, you need to have that recursive spec. And that's the contract, you can rely on when implementing your algorithm. So some kind of programming by contracts. But it's very powerful, especially in more complex situations. Okay. So when you prove correctness, then you're going to you're just going to try to argue that the algorithm satisfies your contract by induction on n. Say, oh, what about n equals 1? It says that I'm supposed to return the sorted list. Oh, that clearly it does. Okay, what if n's bigger than 1? Well, given by induction that it's going to do the first and second half correctly, and I've already shown that merge will correctly output the thing, okay, then the overall output's going to be okay. All right, I think we have it right. Okay. So, yeah, I mean, if you wanted to expand out all the recursive calls, the algorithm will be kind of looking like this. But you really shouldn't think about it this way. In fact, maybe I shouldn't have shown this picture, but I think I once spent a long time on it, so I didn't want to delete it. Right? So ultimately, if you followed all the recursive calls, it is doing something like this. But this is really the wrong way to look at it, right? This is way more complicated if you're comfortable with induction. Okay. So, okay. So besides correctness, which follows from induction, there's this issue of running time, right? We want to make fast algorithms. Initially, the goal is to do better than n squared. Okay. So we're going to model things mathematically. So when I'm declaring the running time, the first step is to just define something, right? So I've written, T of n, that's going to be an upper bound on the input of size n. Okay. And now I'm going to analyze T of n, but I've also declared what T of n is, right? I've given some semantic meaning. Okay. And now I want to try to model this thing, right? So I'm looking at some algorithm. I think the algorithm's on the right. I'm not sure if it's easy to see, but the algorithm is on the right, and I want to try to upper bound the running time, right? So in other words, I have to come up with some kind of formula. I want to quantify this. So, all right, let's just go for it, right? T of n is equal to, right? Now, our algorithm sort of has two cases. Okay. The base case is when n is at most 1. How long does the algorithm take when n is at most 1? Yeah, just a constant. Correct. O of 1 or just 1, either way. So the more interesting case then is when n is bigger than 1. How long does it take when n is bigger than 1? I'm not asking for like the actual answer, just how do I model, right? I'm trying to set up the relationship, and then we can analyze the system of equations that we come up with. So how long at some level does it take?
The sum
Well,
of
we
the
can go through.
the sum of the two recursive calls that we are taking, like T of 1 to m and T of m plus 1 to n.
Right. So, okay. So this step is pretty simple. This just takes constant time, right? Now, this step is a recursive call to some input of size roughly n over 2, right? Okay. And how long does it take to do the input of size n over 2? Well, I've already declared it, right? So this is, by definition, T of n over 2. Here I'm being kind of exact by including the floor. And this next step is looking at the other half, which I guess is rounding up. It'll be Tn over 2. Okay. But there is one more step. How long does that take? Right, linear time. Okay, so you just go through. So we have this, our recursive algorithm, maybe not surprisingly, has a recursive formula, which I'm being careful, more careful than necessary, would look like this. Okay. Sorry, I'm missing a floor. Let me write this out. Right. Now, I put in the floor and the ceiling as a first step, just to be precise. But in any kind of situation like this is really the same as, I know it's not good for a teacher to say really the same as, if I didn't worry about the floor. So that would be 2 times t n over 2 plus the go of n. Certainly this would be correct if n was even. This would be exactly what it is. When n is not even, when n is odd, it's off by 1 or something. Okay. There's several ways to justify doing this formally, and I wrote about it in the notes, but I want to instead on this equation and trying to solve it. Okay, so whenever you have a floor or a ceiling, or if you were in a situation of like n over 2 plus 1, this plus 1 is not significant and it can be dropped. And you can look at the notes to justify this. Okay. Certainly this is true if n is a power of 2. So at the very least, you can imagine taking a list that's not a power of 2, appending a bunch of zeros or something, sorting your power of 2. But that's very late. You don't have to actually even do it this way. All right, this can be justified more directly. It's just not super fun to justify it as a class. Okay, so, all right. So I'm looking at this formula, right? So what we've done is we've modeled our running time, right? I said, oh, T of n is going to be a running time of size n. And I know that for, very small numbers, it's just some constant amount of time. And otherwise, I have 2 subproblems of size n over 2 plus linear work. Okay. And how do I analyze this? So in this class, we're always going to use something called a recursion tree. And what a recursion tree is going to do is it's very versatile. You can use it to also rederive some of these formulas that you see on the internet, but I'm not going to recommend these formulas because that's like teaching math by teaching you how to use a calculator. There's no point in doing this. So I'm going to teach you how to actually analyze these running times. Okay. So what I do is I actually draw a tree that models all of the subproblems. Okay. So this is sort of like the input, the original problem, the root problem, right? And here's sort of like, oh, the top half, in the recursive calls, and here's the bottom half. Okay. But I've drawn a tree, and it already sort of has observed that each problem has 2 subproblems. Okay. And what I do is I just write down, oh, what is the size of the subproblem? In each of these nodes, right? And what's happening is you can see that I'm visually imagining, right? This sort of tells you a little bit about what's going on, right? It's kind of visualizing all the recursive calls. Okay, so all I've done is just help myself visualize the problem sizes. Okay, now let's go through and say, okay, how long does each subproblem take? So the root problem, excluding the subcalls, takes linear time, right? So there's about n work from this subproblem. Okay, now let's go to that second level. So this will be about n over 2 work, and this will be about n over 2 work, all right? The total running time for the merging. Down here, each of these are going to take n over 4. Of course, we're doing something that takes linear time outside the recursive subcall, so it's a little more straightforward, but this is not always the case. Okay. Now look, what I can do is I can add up the total amount of work, excluding the recursive subcalls at each level of this tree. So the first level is pretty easy. It's just n because there's one problem. But what about the second level? I have a couple of different subproblems, each generating some work, but what does it add up to? N, right? At the next level, I have 4 subproblems now, but they're all generating n over 4 work. So 4 times n over 4 is going to give me n. In general, if I'm like 10 levels down, I'm going to have like 2 to the 10 subproblems, each of size n over 2 to the 10, each generating n over 2 to the 10 work, right? So each of these levels are going to look like 2 to the I times n over 2 to the I, which is n, right? So every level is generating linear work, right? Even though there's like a myriad of these recursive subcalls, we have sort of found this sideways way of looking at it to kind of account for what's going on across all of these subcalls. So I now know every level takes n time all added up. So all that's left is to count how many levels, right? So how many levels do we have? Well, again, because this is sort of like the binary sort game, right? The binary searching game, where each time the problem size goes down by 2, factor of 2. So the number of levels is how many times do I have to divide by 2 before I get to the bottom. Okay. So that means if I add all of this up, if I add up all the work across all the levels, what do I get? That's right, n log n. That's how we do a recursion tree. Here's maybe a prettier one that I did ahead of time. Okay, good. So we analyze merge sort. All right. Any questions about merge sort? I know many people have probably seen it before, but still. It's hard for an algorithms class to skip. Yeah.
Professor, I still couldn't really incorporate what's the use for that 2t n over 2 plus all of n. Like in the recursion tree analysis, I don't think we used any of that from it.
Oh, okay. So at some level, yeah, let me annotate this then. So we have this, right?
Yeah.
So when we said that this took n work, this is sort of that big O of n.
Mm-hmm.
And then down here, you see the 2 recursive subcalls. Here's the Tn over 2. Here's the Tn over 2. So once I modeled this and I wrote it down first, and merge sort's pretty symmetric, you know, because it's 2 Tn over 2, but there'll be other times it'll be like n over 2 plus n over 3 or whatever, right? It won't be so straightforward, but we'll do more complicated ones over time. But once I wrote down the equation, then I say, oh, okay, here's a tree where I try to take that equation and visualize it.
Mm-hmm. Professor, then where did all of n's go?
I hid them. So, okay, so this might be some Cn, right? Some constant, maybe 5n, right? So really there should be Cn here, Cn there. And then there should have been, 2 times Cn over 2, and then you get Cn here. So in general, I could have written it doesn't matter too much. I could have written something like this, and that would have been correct up to constant factors, and that would have also been okay, maybe less confusing. Yeah. I agree. It's going to take a little getting used to with the big O notation, but it is in fact quite robust. And then what it lets us do is really focus on the big algorithmic differences that make a difference in the big O notation. That's where the big fun ideas are. Good question. Okay, awesome. So that's sort of our first formally done non-trivial algorithm, which maybe everyone had seen before, but oh well. Okay, so here's maybe something that less of the audience has seen before. This is a very funny question. Lower bound for sorting, right? So we got this n log n running time, but is it the best possible running time? That is our new question. Okay? So the question always is, can you do better? N log n was a big improvement, but I don't know, we can verify an n. So now we're kind of in between n and n log n. Okay? And we're trying to understand this problem. So, can you do better than n log n? Or alternatively, is n log n the best you can do? Is it an optimal algorithm? If you can prove your algorithm's optimal, that's quite good, right? So our goal now is to try to prove a lower bound for all sorting algorithms, right? I'm going to try to prove that any correct algorithm has to take at least such and such and such a time, right? This is quite odd. To get a proven upper bound, to say, oh, you can sort in n log n, I just have to generate one algorithm that takes n log n time. To prove a lower bound, I have to somehow argue that any algorithm, including any algorithm I've never thought of before, has to take such and such a time. So that's quite an exercise in abstraction, right? So how are we going to do this? So what we're going to do, and maybe a really key conceptual step, is to find a good model. Okay. So we assumed our input was only comparable elements. So we're going to be in a comparison model, right? Where in a single step, the algorithm can compare two of the inputs and say, oh, is one bigger than the other? Okay. And then rather than trying to lower bound the running time of any particular algorithm, we're going to try to argue that any algorithm has to use a certain number of comparisons to be able to conclude it's correct. And if that's the case, then assuming that comparisons take at least constant time, then any algorithm has to have at least that much time as well. Right? But it's the setup that's quite non-trivial, right? How do you even set up a lower bound? Well, here's one way. Okay. All right, nothing here. Okay, so here's how we're going to try to argue. So again, the challenge in imagination is that I'm not fixing any particular algorithm, and I'm going to talk about sorting algorithms generally, right? Which is not obvious how to do it, but here's how we're going to do it, right? So suppose an algorithm makes k queries for some number k, right? So it asks a bunch of questions. They may depend on each other, right? Obviously, based on how the first query went, that's going to determine the second query, and the outputs from the first two queries will depend give the third and stuff like this, right? And it's going to make these queries, and then it's going to output some list. That's all I know, right? All I know is going to make k comparisons. They might be adaptive, and it's going to output a list that it claims to be sorted. Okay, but the only input coming into the system is the output of these queries. Right? So ultimately, the list of n elements it outputs is completely a function of those k queries. Right? The yes, no, yes, no, yes, no. That transcript, the list follows deterministically. Because that's the only input coming into the system. So, okay. I know that the output is a function of the answer to these k queries, these yes-no queries, right? Okay. Now, each query can have how many outcomes? Two, yes or no? Okay. So if I have k queries, each has two outcomes. How many possible outcomes can this algorithm generate as a function of k? A 2 to the k. Right? So at most 2 to the k inputs, at most 2 to the k outputs, if it's a function of the input. Okay, that's it. Notice that we really didn't assume much about the structure of the algorithm, just that it makes comparisons. This will go faster than you would think. All right, so you can output 2 to the k lists, but how many possible lists? I mean, how many possible lists are there? N factorial, perfect, right? So n factorial is, n, right? Because any of the n items can come first. Once that item comes first, you have n minus 1 item choices for the second, times n minus 2 for the third, so forth. The last one, there's no choice because you've already slotted everything else, right? So you need to be able to output n factorial different lists. Okay. So what does that tell us about the relationship between k and n? To be correct, you have to be able to output any of the n factorial different lists, and you can only output 2 to the k different things. So we have this, right? A correct algorithm that makes k queries must have 2 to the k is at least n factorial. Okay. These are kind of astronomical numbers. So let's try to bring it. I'm really interested in k, right? So let's take the logarithm of both sides, base 2. So that means k is at least the logarithm base 2 of n factorial, right? Again, nothing too complicated, right? And now we just have to deal with this, and then we can all go home. So I just want a lower bound n factorial. What's a lazy, easy, gonna get you out of here quickly, lower bound for n factorial? Because n factorial is a bit messy, right? There's fancy ones on Wikipedia, but you won't need those. All right, suppose I told you that this is at least n over 2 log n over 2, which is really trying to say that n factorial is at least n over 2 to the n over 2. Why? Okay. Yes, but so why then? Okay. Well, I know that in this list, if I'm looking at all the numbers bigger than n over 2, there's at least n over 2 of them. Right? So n over 2 times n over 2 times n over 2. So you get n over 2 to the n over 2. That's a very lazy lower bound. Right? But, okay, you showed that k has to be at least n log n up to constants. Right? Even with this very sloppy lower bound for n factorial. Okay, so we conclude that k has to be at least n log n up to a constant, right? Okay, so let's wrap up. So in a comparison model, you need at least n log n comparisons. So what have we accomplished then, right? We have an upper bound of n log n from merge sort and a lower bound of n log n from this kind of simple, 2 to the k is at least n factorial type argument. Okay. Now, of course, any lower bound is at most any upper bound by definition of lower and upper. Okay. But we've now shown something else, right? We've shown that an upper bound is less than a lower bound up to some constant, right? N log n on one side is at most, 1,000 times the n log n we got on the other. Okay. So what does that tell us, right? When you get the upper bound and the lower bound so close to each other, that tells you that actually both of the answers are correct. The upper bound can't go any further down because it's already hit the lower bound. Okay, so they mutually certify each other to be optimal. That's the real key thing, right? Upper bounds are interesting, lower bounds are interesting, but you put them together, you really understand the problem. Okay, so that's another point of emphasis in this class, this sort of other side of the coin, but it'll really help you understand the whole coin. Okay, so n log n turns out to be the right answer for sorting, at least in the comparison model. Okay, so that's the kind of stuff we'll be doing in this class. All right, I'm a little bit over, and that is a natural end. So next time we'll have some fun with induction.